complication is when the differential equation is what's called non-homogeneous. So homogeneous means the thing on the right is equal to 0, but you can also have an external force. Now I could write this with ABCs, but let's instead of A, let's use mass times second derivative of displacement, which is mass times acceleration, plus lambda times x dashed of t. If you take that away from both sides of the equation that we end up with, that's a damping force. Similarly, we have a spring force, and say if it's now, what we've looked at in the previous lectures is if it's equal to 0, but what if there's an external force? Now we kind of make a distinction between the damping force and the spring. So imagine the door closer, they're kind of a part of the system, and then someone coming pushing the door or whatever, that's an external force. Okay. In many contexts, pretty much all the contexts in this chapter, 5t is some external force. Now we've got a big theorem here which says that if you have see, we've got a big story here, is that it's a big long story. I think it's better just to do some examples rather than showing it. But I will just say one thing, that if you have non-homogeneous, so if you got something non-zero here, first you solve it equal to 0. And then you find a particular solution. So what you have to understand to kind of figure out what the hell this is kind of rabbiting on about is that these differential equations have infinitely many solutions, because you need a different solution for each value of the initial displacement and the initial velocity. So if you just write down a differential equation like this above without specifying, say, the initial value of the displacement and the initial speed, there's infinitely many solutions. So the theory actually says, though, that the infinite part of the solutions is already in this homogeneous. So the infinitely many solutions occur here. And this is about related to the A and the B that we were talking about previously, which we'll see in examples. And then this is just one solution of the thing. And it turns out that if you add together the solutions of the homogeneous, so that's you solve it equals 0, that's where you get your infinitely many solutions, and then you just add one solution of the actual problem you're looking at, and then you get all of them. So I think that's probably something that's probably better explained with examples, as we will do. Now we just need a little bit of revision here of differentiation in time. Okay, so the first thing, if you have a constant times a function, how do you differentiate it? You fix the constant and then you differentiate. So what I mean by that is constant times function, fix the constant, differentiate. Then you have the product rule, which you should know, and then the chain rule. Now the other way that I would write the chain rule is something like this. So you've got, I should probably do it with t, because yeah. So you got an outside function and an inside function. And the chain rule says you differentiate the outside function, you evaluate it at the inside, and then you multiply by the derivative of what's inside. And that's what this third thing is actually saying. So it's the derivative of the outside, evaluate the inside, times the derivative of what's inside. Now, a common misconception that students have is that the constant rule, the first thing, so yeah, constant rule is the first one, is that the constant rule here cannot be correct because the derivative of a constant is 0. Now, it is true that the derivative of a constant is 0, but if you're differentiating a constant times a function like here, there's no contradiction here, because if you want to differentiate a constant times a function u of t, what you can decide is like, okay, it's a constant function k is, and just do the product rule. So if you do the product rule here, you'd say it's the first thing by the derivative of the second thing plus the second thing by the derivative of the first thing. And indeed, the derivative of k is 0. And so you're left with the constant times the derivative, and the second term there is just 0. So there's no contradiction to saying when you differentiate a constant times a function that you fix the constant and differentiate, and saying that the derivative of a constant is 0. Like, I'm not saying that, like, a different scenario is if you're differentiating a function plus a constant. That's a different scenario. If you've got a sum, you just differentiate term by term. So the derivative of u of t is u dashed of t, and the derivative of a constant there is 0. But that's not the same. That's a constant added is not the same as a constant multiplied. Okay, so some examples here, just to kind of remind you of your differentiation. So the derivative here of y, so we're going to fix constants, and we're going to have to differentiate sine of t using the chain rule. So the chain rule says you differentiate the outside function. The outside function here is sine of x. The derivative of sine of x is cos of x. The chain rule then says evaluate that, the derivative of the outside, at the inside. And then the chain rule says multiply by the derivative of what's inside. And so I should tidy that up. I end up with, now one small thing, you can't multiply the 2t by the 2. This just doesn't make sense. It's cos of 2t times 2. So rather than people getting confused by that, you should do a by 2 by cos 2t, and then if you want, a by 2 is the same as 2 by a. So 2a times cos 2t. Okay. Do another example. Think. Differentiate this using the constant chain rule. So the thing that would catch people here is maybe the derivative of cos is minus sine, and I'll show you where it becomes a slight issue for us. So the derivative here, fix the constant a. Now what we're tempted to do is say, okay, we're differentiating cos of 3t. So the outside function is cos of x. So the derivative of cos of x is minus sine of x. Now it should be a times minus sine of x here. Let's finish it off. Chain rule says evaluate at the inside, which is 3t. And the chain rule says you must multiply by the derivative of what's inside. Derivative of 3t is 3. Now this looks like a minus sine 3t, but we should be a bit careful and maybe for the moment just put a bracket around that. So it's a positive thing by this negative thing, and plus by minus is minus. And you got a by minus by 3, which is minus 3a times sine of 3t. Okay, and then here you got to recognize that this is a product, at by e to the minus 3t, and you want to do carefully do a little product rule. First thing u by second thing v, and the product rule is on the previous page. It says the derivative of a product is the first thing, which is at, times the derivative of the second thing. Now, you might need to get your little tables going. I think let's make a note there. I will try and send you tables if you haven't got your own. But one of the things you'll see in it is that the derivative of e to the ax is equal to a times e to the ax. Now that itself can be shown using the chain rule, but we'll just take it as in the tables. So the derivative of e to the minus 3t is minus 3 e to the minus 3t. And we've got a similar thing here. We might just bring in a little bracket there to make things a bit clearer for us. So that's the first thing by the derivative of the second thing plus the second thing by the derivative of the first thing. Now for differentiating at, what I'm going to do is I'm going to fix the a, and what's the derivative of t with respect to t? 1. And then we can tidy this up if we want. We've got a by t by minus 3 by an exponential. They're all ultimately just numbers, so we can multiply them together in whatever order we want. And I like minus 3 by a by t by e to the minus 3t. And then the other one, well, a by 1 is just a plus a times e to the minus 3t. If differentiation is an issue for you, this might be a challenging chapter. Not the next one, funnily enough. This one will be. And what you can do is you can go to here, and I've got some practice for you for differentiation. Okay, so now let's do some full-blown examples. Now these will take a while, okay? They're not particularly easy. So find the general solution of the ordinary differential equation. So the general refers to So you got a differential equation, it's a damped harmonic oscillator, and you've got an increasing external force. Now the weird thing here is that like t is time, but here the force, it doesn't have units of time, this thing. This is a force. And the force just happens, the value of the force, the magnitude of the force just happens to be the same as the time. So the force looks something like this. Okay. It's increasing. Yeah. Now, if you think about it, the door, you might get into a bit of bother here. If you think more about a spring with a damper on it, it'll make sense. So this is, you've got a spring and someone essentially is pulling the spring, but with a larger and larger force. Now you should know that you won't be able to keep applying a larger and larger force to a spring. Eventually it's going to leave what's it called? The elastic regime, it's going to go into the plastic regime. So the solution we find is actually only really valid for a certain period of time. And what we're going to see is that the displacement of the spring is going to go to infinity. Now the infinity that we find isn't the plastic one. It's kind of it's assuming that the spring never goes plastic, which is nonsense. Okay, so let's see. So the theorem above says you must find, it says that the general solution is the homogeneous plus the particular. Now the homogeneous means solving it equal to 0. So I'll write down the homogeneous system. So the homogeneous system would be second. Now I'm gonna flip between the D notation and the double dash notation. So we're looking at x double dashed of t plus 3 times x dashed of t plus 2x of t equals 0. So we have to solve this first. So the solution of this is the homogeneous solution. So we find this. So how we do this is we find the roots of the auxiliary equation. So look at the ABC and form an equation. Now maybe just to get the focus right on this, I'll write down the equation. So this is r squared, 1r squared plus 3r plus 2 is equal to 0. I do recommend, because of the next chapter, that we actually factorize these and solve it like that. So I do the a by the c is the 1 by 2 is 2. And look at the factors of 2. I have 1 by 2, 2r I already have. And the question is, can I rewrite the middle term, the 3r, using a pair of those? Oh yes, I can. So I end up with r squared, and I rewrite the 3r as 1r plus 2r, and we're left there with the plus 2 equal to 0. Now last time I used to leave out the equal to 0, but here I'm going to include it. Now let's factorize this by taking something common out of r squared and r, which is r. What are you left with? Well, r plus 1. And then take something out of 2r plus 2 that leaves r plus 1 again. The answer is 2. Now take out something common out of both of these, which is r plus 1. And so you've got r plus 1 times r plus 2 equal to 0. So you've got two numbers now, r plus 1 and r plus 2 are two numbers that multiply together to give you 0. The only way that can happen is if one of them is 0. So therefore, r plus 1 is equal to 0, or r plus 2 is equal to 0. And now being ultra pedantic, you want to get rid of that 1, you take away 1 away from both sides. And then here, you want to take away 2 from both sides. You end up with, the first one will give you r is equal to minus 1, and the second will give you r is equal to minus 2. And maybe what I wrote down there is kind of nonsense. Right, so these are real distinct. So this is the easiest case. So in this case, the general, this is now not the general solution, this is the homogeneous. So the homogeneous is the general solution of the homogeneous, okay? So general means you capture all the possible initial conditions. Homogeneous means equal to 0. And in this case, this means the xh means the general solution of the homogeneous. So xh of t equals, we know we have a solution e to the minus 1t. We know we have a solution e to the minus 2t. We know that multiplying solutions by constants give us more solutions, and we know that adding solutions together, and this is the homogeneous solution. So, and because the a and the b are there, that's where you capture the infinitely many solutions. Right. Now the question becomes finding a particular solution. So the philosophy will be, and we'll make it more precise after this, is to pick a possible solution that looks like the external force. Like if you look at the external force here, so it's increasing, increasing, increasing. Wouldn't you possibly expect that a solution of the system could see? So imagine the force. So maybe it's increasing by every second. It's increasing by whatever, a millinewton or whatever. Couldn't you see? So it's going 1, 2, 3. So imagine you're pulling the spring stronger and stronger and stronger. Now imagine after a while, couldn't it be the case that if you kept pulling the spring with increasing force, perhaps could it be the case that the spring itself would just come with you? Now maybe you think that the force would have to grow faster, but anyway, so this is what we're going to do. We're going to try and take the particular solution. So this is just one solution of the whole thing that maybe it looks like the force. Now the force is a line, so we're going to try mt plus c. Actually, I don't think I'm going to use those symbols, but they'd be good symbols. It's going to be like a line is mx plus c. We're going to use ct plus d. So the c and d rather than m and c. Okay. So the philosophy will be, and we'll make it more explicit, is to pick a function that looks like this. So it's a trial solution. Now we are chancing our arm. If it works, it works. And this is where the undetermined coefficients is going to come. That's what the name of this chapter is going to come in. So can we find values c and d? These are the undetermined coefficients. These are the undetermined coefficients. Undetermined. And this is the big principle I was talking about. We know what the solution should look like. So we basically just try and force it to solve the system. Okay. So let's see. Now what we have to do probably is just, I have to pause this and write down the equation for myself. So I'll write it up the top here as well in a very gentle form. The second derivative plus 3 times the first derivative plus twice what we're looking for equal to t. And we're going to try something that looks like t. So you might just look back at my notations here. Are they okay? Yeah. So the trial solution, t for trial, we're going to chance our arm with this, is to get something that looks like t, ct plus d. Now it looks like in the sense that it's a straight line. Okay. Now, looking at the first derivative of ct plus d, let's differentiate it term by term. Fix the c, it's constant, and the derivative of t is 1. So that's c by 1, that's c, and the derivative of d, a constant, is 0. So the first derivative is just c, a constant, that we haven't figured out what it is yet. And then the second derivative, you differentiate that again. Now maybe I'll just slow down and do that over here. So you have ct plus d. Let's differentiate it. How will I write that? So let's just write this as xt, therefore x dashed of t. So differentiate ct plus d. C and d are constants, we just aren't specifying what they are. So when you're differentiating ct, fix the c. What's the derivative of t? 1. Plus, what's the derivative of constant d? 0. And c by 1 is just c. And now we'll differentiate again. Remember, the second derivative means you differentiate the first derivative. And the first derivative is a constant c, so the second derivative is 0. Now we're going to try and force, similar to what we did before, we're going to try and put the trial solution in there, the second derivative in there, the first derivative in there. We're trying to force this to work, and we'll see what happens. So second derivative of the trial solution plus 3 times the derivative of the trial solution plus twice the trial solution is equal to what? So the second derivative is 0, we calculated that, plus 3 times the first derivative is c, we've calculated that, plus twice the trial solution. The trial solution is ct plus d. And we're going to tidy this up a little bit. We're going to put the t's together and the constants. So the t, you got 2 by c by t. And then you've got 3c plus 2d. And we want that to equal, I'm going to put an exclamation mark, so we want to force this to be equal to t. Now there's different ways of thinking about this, okay? I'll maybe explain 3 of them. So t on its own is actually 1t plus 0. So if you want these to be equal for all values of t, actually I've actually only got 2 ways, but then I'm going to say what I think. So I want to find the values of c and d that make these two things on the left and the right equal for all values of t. Now, is it possible that there's no pair of values that does it? Yes, but we won't worry too much about that. It'll happen. If it happens, it happens. It turns out what we can do is we can compare coefficients. So if you look at the t on the left, it's multiplied by 2c. And if you look at the t on the right, it's multiplied by 1. If you look at the constant term on the left, it's 3c plus 2d. And on the right, it's 0. And it turns out that if you can force 2c to equal 1 and 3c plus 2d to equal 0, then is it not obvious that they're equal for all values of t? If it's not obvious, what you can do is you can say, okay, substitute in values of t into both sides, substitute in t equals 0, you'll end up with the green bit, and maybe substitute in t equal to 1, you'll end up in a moment with the red bit, or you could differentiate first with respect to t and then sub in t equal to the, well, you could just sub in t equal to 0 and then differentiate. Well, anyway, however you want to do it, and maybe there's comments down below, yeah. You just compare coefficients. So we want 2c, the red bit, to equal 1, so c is equal to half. And what do we want to do with the green bit? We want 3 times c, which is a half, plus 2d to equal 0. 3 halves is 3 over 2. We can take that away from both sides. So we want 2d to equal minus 3 over 2. And then you want to get d on its own. It's multiplied by 2, so divide both sides by 2. And you get d is equal to minus 3/4. Okay. Now, what you can see, if c is equal to half and d is equal to minus 3/4, then this yoke is a solution. Now, it's probably worth going back to the previous thing. If you compare the slopes, the slope of this is actually smaller than the external force. So the slope of this is a half. So actually, the xp isn't parallel to the force. It is a line. It's kind of more like that. So the force is actually growing faster than this particular solution. Then the theory says, if you want to get all the solutions, you add together the homogeneous, which is on the previous page, down the bottom, defined with -1 and -2. Plus the particular, which is this half t minus 3/4. So, and it turns out that that's how you get all the solutions. So this is the homogeneous part, say xh, and the particular part xp. And theoretically, you can show that that's all the solutions. The kind of infinity to capture all the possible initial displacements and initial velocities is captured in the XH bit. Okay, so the problem of what to pick is kind of given by this thing. Now, in an exam situation, you have to kind of understand the principle or kind of deal with the, or kind of, I don't really want people learning off the box, but in general, in principle, this is what you would do. Now here it's open book assessment, so you don't have to know so much, but just take the philosophy that if the external force is a constant, the trial solution should be a constant. If the external force is a line, the trial solution should be a line. And we can actually push this a bit further. If the external force is, I'm just going to write Q for quadratic, then the trial solution should be a quadratic. If the, maybe I should write a bit more than Q, quad, same as a parabola. And then a pattern goes on. And then this one, if the external force is a wave, you should try a wave. If the external force is an exponential, you should try an exponential. The thing about it is like you might see slight differences. The difference between, say, the PT, so I'm just going to talk about this. The difference between this and this is they're both lines. They look different. It's just the PT line cuts the origin at 0. The other one doesn't. Similar kind of relations between them. So, and looking at the wave ones, well, what's going on with the waves is that this is a wave that starts at its peak. And this is just saying, well, I'm not saying that the wave is starting at its peak or trough or anything like it. That's the difference between them. Okay. Now, what is in common, there's a little bit more in common if we get down to the waves. So what's a little bit more in common between them is this is kind of the angular frequency, basically this Q. So basically imagine a spring and someone has an oscillating force. The spring is eventually going to go with the same frequency. That's why the Q's should be the same here. And the exponential is a bit maybe harder to explain, but the Q's are the same. Okay, so now we kind of know the theory. I think we'll leave some of these examples to the next lecture.